Fine. Let's start. Most people assume the dangerous parts of the universe are safely somewhere else. A black hole in a distant galaxy. A supernova in some other arm of the Milky Way. Something separated from us by a comfortable number of zeros. They're not. Some of the most lethal environments we know of are right here, in our neighborhood, in our atmosphere, in the rock beneath the ocean. And at least one of them you can see with your naked eye on any clear night. Here are 10 of them. Number 10. The spacecraft graveyard above South America. There is a patch of space roughly 200 kilometers above the South Atlantic Ocean, sitting over Brazil and the surrounding region, where something is wrong with Earth's magnetic field. The field isn't uniform. It's generated by a churning mass of molten iron in Earth's core, and that core isn't perfectly centered. The result is that in one specific region, the inner radiation belt, a donut of high-energy particles that normally sits comfortably above 1,000 kilometers, dips down to almost 200 kilometers, closer than some satellites orbit, close enough that spacecraft passing through it get pelted by radiation that would take years to accumulate anywhere else. We call it the South Atlantic Anomaly. The Hubble Space Telescope shuts its sensitive instruments off every time it crosses over it. The Chandra X-ray Observatory was placed in a deliberately high orbit, partly to avoid it. The Integral Space Telescope was designed from scratch around the problem of not spending too much time there. And then there's Hitomi, Japan's Hitomi X-ray Telescope, launched in February of 2016. It was a $270 million spacecraft, state-of-the-art, carrying instruments that could peer into the most energetic events in the universe. Months into its mission, it broke apart, a cascade of failures, likely initiated, at least in part, by software errors triggered during a pass through the anomaly. It was declared a total loss. The mission was over. But here's the thing. Hitomi is not the weirdest part of the story. The weirdest part is this. The anomaly is expanding. It's drifting westward. And recently, the region of minimum field strength inside it has split into two separate lobes, creating two distinct dead zones instead of one. Nobody is entirely sure why. Astronauts on the International Space Station know when they're crossing it. Not because of any alarm, because they see flashes of light, not through the windows, with their eyes closed. The radiation passes through the hull, through their eyelids, directly into the optic nerve. Phantom photons. Stars that aren't there. The most dangerous radiation environment in the Earth-Moon system is not on the Moon, or somewhere in deep space. It's sitting above the South Atlantic, 200 kilometers up, and it's quietly getting bigger. We'll come back to what that might mean. Number 9. The Death Star that was probably pointing at us. In 1999, astronomer Peter Toothill was working with the Keck Observatory in Hawaii, observing a binary star system called Wolf-Rayet 104, about 8,000 light-years away in the constellation Sagittarius. What he found was beautiful. The two stars were orbiting each other every 8 months, and the collision of their stellar winds was producing a spiral of glowing dust. A pinwheel, spinning slowly in the infrared. He stared at it for a while, and then he said something that got a lot of people's attention. I used to appreciate this spiral just for its beautiful form, but now I can't help but twinge a feeling that it is uncannily like looking down a rifle barrel. Here's what he meant. The pinwheel appeared to be rotating face-on toward Earth, like someone spinning a garden hose directly above your head, and you're looking straight up at it, which would mean the rotational poles of the system, and of the Wolf-Rayet star at its heart, were aimed directly at us. Why does that matter? Because one of those stars is going to die. Wolf-Rayet stars are, as astronomers put it with remarkable understatement, ticking bombs. When a massive, fast-spinning star collapses and dies, it can produce a gamma-ray burst, two focused beams of energy so concentrated that they can strip the ozone layer off a planet from thousands of light-years away. the system got a nickname: the Death Star. For over 2 decades, the question hung in the air. Were we in the beam? Then, in 2025, astronomer Grant Hill at Keck finally measured the actual orbital velocities of the 2 stars, and the answer was probably not. The orbital plane is tilted at least 30 to 40 degrees away from our line of sight. We're not in the crosshairs. Almost certainly. But here's the thing. The dust spiral still looks perfectly face-on. The geometry that was supposed to prove we were in the crosshairs turned out to be an optical illusion produced by a process nobody fully understands yet. The feature we used to assess our safety was wrong. The actual aim of the system is still being worked out. Probably safe. Probably. For a star that will explode sometime in the next few 100,000 years, that's not the most satisfying answer. Number 8. Apophis, the rock that will pass. Closer than our own satellites. On April the 13th, 2029, less than 4 years from now, an asteroid named Apophis will fly past Earth. At its closest, it will be approximately 32,000 kilometers away. To put that in perspective, many of the satellites we use for GPS and weather forecasting orbit at around 36,000 kilometers. Apophis will pass closer to Earth than our own communications infrastructure. It will be visible to the naked eye from Africa, Europe, and Asia. A rock 370 meters across, sailing silently through the sky, named, appropriately, after the Egyptian god of chaos, darkness, and fire. When Apophis was first discovered in June of 2004, astronomers calculated a 2.7% probability that it would hit Earth in 2029. That is the highest danger rating ever recorded for an asteroid of that size. The entire planetary defense community essentially held its breath while better observations came in and the probability dropped. The 2029 impact was eventually ruled out. But the story didn't end there, because the 2029 flyby introduced a new problem. Earth's gravity, during the close pass, will physically alter Apophis's orbit. And for years the question was, alter it into what? Astronomers identified what they called a gravitational keyhole, a region of space a few hundred meters wide that Apophis would need to pass through during the 2029 flyby for its new orbit to be set on a collision course with Earth in 2068. A few hundred meters. In 32,000 kilometers of close approach. The odds of threading that needle were small, but they weren't zero, and they couldn't be fully ruled out until 2021, when new radar observations finally collapsed the uncertainty. The keyhole is clear. We're safe. But sit with the concept for a moment. A zone a few hundred meters wide in the darkness of space, and if a rock the size of a skyscraper happens to pass through it, we get a date with oblivion in 40 years. The universe doesn't need to aim very carefully. It just needs to get lucky once. Number 7. The star that faked its own death. Eta Carinae is one of the most massive stars we know of. Sitting roughly 7,500 light-years away in the constellation Carinae, it burns at approximately 5 million times the luminosity of our sun. It is, to put it plainly, obscene. And sometime between 1837 and 1858, it went wrong. During a period astronomers call the Great Eruption, Eta Carinae brightened dramatically and became the second brightest star in the night sky, outshining everything except Sirius, despite being 800 times farther away. For a time, it was visible in daylight. It ejected several times the mass of our entire sun into surrounding space. The shell it threw off is still visible today. We call it the Homunculus Nebula. And then, it didn't die. It dimmed. It faded. It's been brightening again since around 1940. Whatever it did it without finishing the job. In 2001, Physicists Arnon Dar and Alvaro de Rujula at Technion and CERN ran the numbers on what happens if Eta Carinae eventually produces a gamma-ray burst pointed at Earth. The result? The hemisphere facing it would experience skies brighter than the sun for several seconds. Then wildfires on a continental scale. Then years of ozone depletion as the atmosphere chemistry rebalances. The current scientific consensus is that Eta Carinae's rotational axis is tilted about 45 degrees away from our line of sight, so a direct beam is considered unlikely. The axis isn't aimed at us. But here's the thing. We recently said the same thing about WR-104, and that turned out to be an optical illusion. Eta Carinae has already done something we don't have a good model for. It erupted with enough energy to fake a supernova, throw off multiple solar masses of material, and survive. We don't fully understand what it did or why. A star capable of that is a star that can still surprise us. It's sitting there, 7,500 light-years away, quietly brightening. Number 6. The solar storm that almost ended the modern world. July the 23rd, 2012. Our sun erupted. The coronal mass ejection that launched that day was enormous, Carrington-class, meaning it was in the same category as the most powerful solar storm in recorded history. If you're not familiar with the Carrington event of 1859, here's the short version. It was a solar storm so powerful that telegraph operators reported sparks flying from their equipment. Some received electric shocks, and the aurora borealis was visible as far south as Cuba and Colombia. It was remarkable in 1859. If the same event happened today, it would be catastrophic. Back to 2012. The July storm erupted and tore through space at roughly 3,000 kilometers per second. It struck a NASA spacecraft called Stereo A that happened to be in its path and measured its strength. The data was striking enough that physicist Daniel Baker of the University of Colorado later went on the record at a NOAA space weather workshop and said simply, if it had hit, we would still be picking up the pieces. A Lloyd's of London risk analysis estimated that a Carrington-class storm hitting Earth today could cause between $0.6 and $2.6 trillion in damage to the United States power grid alone. The high-voltage transformers that carry electricity across continents take years to manufacture. They don't sit in warehouses. There is no spare parts system designed for losing hundreds of them simultaneously. Earth missed this storm by 9 days. 9 days earlier in its orbit, and we'd have been directly in its path. Here's the thing that makes this worse. The Carrington event was once considered a once-in-a-century anomaly. New analysis of carbon-14 levels in tree rings, which record past cosmic radiation events with remarkable precision, suggests that massive solar storms may happen considerably more often than we thought. We weren't just lucky in 2012. We've probably been lucky many times without knowing it. We dodged a civilization-altering event in 2012. Almost nobody reported it at the time. Number 5. The radiation storms written in tree rings. In 2012, the same year incidentally, that we almost got hit by that solar storm, a physicist named Fusa Miyake at Nagoya University in Japan was studying the rings of a 1900-year-old Japanese cedar tree. She was looking for subtle patterns in radioactive carbon-14, which trees absorb from the atmosphere and lock into their rings as they grow. Carbon-14 levels fluctuate with cosmic radiation, so tree rings are essentially a historical radiation log preserved in wood. And in the ring from 774 AD, she found something she didn't expect. A spike 12% higher than normal. That's roughly 20 times the typical annual variation from cosmic radiation. She thought it was a measurement error. It wasn't. The same spike showed up in trees from Germany, Russia, the United States, Finland, New Zealand. Whatever happened in 774, it happened globally. Every tree on Earth recorded it. Since that discovery, 5 more events have been identified in tree rings. in 993 AD, 660 BC, 5259 BC, 7176 BC, and in 2023, a team using ancient logs pulled from an eroded riverbank in the French Alps confirmed the largest one yet, dating to 12,349 BC. The 774 event alone was 80 times more powerful than the 1859 Carrington event. 80 times. If something like that hit today, it wouldn't just disrupt the power grid. It would destroy global satellite infrastructure simultaneously. Communications, GPS, weather systems, all of it, simultaneously gone. Now here's the thing. We don't know what caused any of these events. The leading hypothesis is an extreme solar particle event, essentially a solar flare of a scale our sun has never produced in recorded history, by a factor of 80. Possible. But the required energy pushes against the edges of what solar physics models say our sun is capable of. Could it be a gamma ray burst? No confirmed source has ever been identified for any of the events. A nearby supernova? Same problem. A Magnetar flare? Plausible for some, but again, no confirmed origin. These events happened. They are recorded in wood on 6 continents. They recur on timescales of centuries to millennia, and we have no confirmed explanation for what causes them. The next one is not a matter of if, it's a matter of when. Number 4. The Magnetar that physically struck Earth from 50,000 light years away. December the 27th, 2004. A neutron star on the far side of the Milky Way cracked. The object is called SGR 1806-20. It's a magnetar, a neutron star with a magnetic field roughly 1,000,000 billion times more powerful than Earth's. A teaspoon of its material would weigh about 1,000,000,000 tons. Its magnetic field is so strong that at half the distance from Earth to the Moon, it would be strong enough to erase the data from every credit card on the planet. What happened on that December day was a starquake, a sudden fracture in the neutron star's rigid crust, triggered by the extreme stress of its own magnetic field. The crack was approximately 5 kilometers long. In the resulting explosion, SGR 1806-20 released more energy in 0.2 seconds than our sun will radiate over the next 250,000 years. And then, roughly 42,000 years later, because that's how long it takes light to travel 50,000 light years, the pulse arrived here. It hit Earth's ionosphere. Measurably. Instruments around the globe recorded the disturbance. The upper atmosphere, the layer we rely on for radio communications and navigation systems, physically reacted to an explosion on the other side of our galaxy. Let's put 50,000 light years in perspective. The Milky Way is about 100,000 light years across. SGR 1806-20 is on the far side of it. This is not a neighbor. This is someone in another country banging on their wall, and our walls shook. Now here's the thing. The nearest known magnetar to Earth is approximately 9,000 light years away. If a burst of the scale that SGR 1806-20 produced happened from within 10 light years of Earth, just over twice the distance to our nearest stellar neighbor, it would have been equivalent to a 12 kiloton nuclear detonation at our doorstep and would have stripped the ozone layer. No known magnetar is anywhere near that close, that we know of. Magnetars are detected primarily by the bursts they produce. A quiet magnetar is an invisible magnetar. On December the 27th, 2004, the far side of the galaxy reached across 50,000 light years and touched our atmosphere. And that was a relatively quiet day for a magnetar. Number 3. The shield is turning off. Earth's magnetic field is not decorative. It is the reason Earth has an atmosphere. Without it, the solar wind would have stripped our air and water into space billions of years ago. It deflects the majority of cosmic radiation that would otherwise be constantly hitting the surface. It is, functionally, the reason anything alive exists on this planet. And it has been weakening for 3,000 years. The field has lost approximately 30% of its strength since humans first started measuring it. That's not a rounding error. That is a sustained, directional decline over 3 millennia. The standard scientific response to this is that it's probably fine. The field fluctuates over geological time, and there's no immediate cause for alarm, which is true. But it's also worth knowing what the field weakens significantly actually looks like in practice. Because we have a case study. 42,000 years ago, Earth's magnetic field didn't just weaken, it nearly turned off. During what's called the Lachamps excursion, the field collapsed to roughly 6% of its current strength. It stayed there for approximately 500 years. During that time, the poles temporarily reversed, meaning if you'd had a compass, it would have pointed south. The ozone layer degraded significantly. Cosmic ray flux on the surface increased dramatically. Atmospheric electrical patterns changed globally. And here is what happened on Earth during those 500 years. The Neanderthals vanished. The last confirmed evidence of Neanderthals in the fossil record corresponds roughly to this period. Australian megafauna experienced rapid collapse, and in multiple regions across the world, simultaneously, with no prior evidence of it, cave art appeared. The first confirmed instances of humans painting on cave walls occur around 42,000 years ago. There's a theory carefully proposed by researchers at the South Australian Museum and the University of New South Wales that the environmental chaos of those 500 years, increased UV radiation, disrupted ecosystems, a sky gone strange with auroras visible at the equator, may have been a forcing event in human cultural development. The event was formally named the Adams Transitional Geomagnetic Event, a deliberate reference to Douglas Adams and the number 42. The scientists felt it was appropriate. Here's the thing. The South Atlantic Anomaly, the radiation dead zone we talked about at the start of this list, may be an early symptom of the same process. In some computer simulations of geomagnetic pole reversals, anomalies like the South Atlantic Anomaly appear and grow in the early stages of a transition. The current anomaly has recently split into 2 lobes. The field continues to weaken. We don't know if we're heading toward a reversal. We don't know how to predict one. What we do know is that it has happened before, and when it did, the world was a different and considerably more dangerous place for 500 years. Number 2. The ocean floor is covered in debris from a nearby explosion. At the bottom of the Pacific Ocean, and the Atlantic, and the Indian, in thin layers of ferromanganese crust, the slow-growing mineral deposits that form across millions of years on the seafloor, there is something that shouldn't be there. Iron-60, a radioactive isotope of iron that is produced in one place in the universe, inside a dying star, in the final seconds before a supernova. Iron-60 has a half-life of 2.6 million years. Any Iron-60 that formed when Earth formed, 4.5 billion years ago, has long since decayed into nickel. What's gone is gone. And yet there it is, on the ocean floor, in layers that date to approximately 2.6 million years ago. As Adrian Malott of the University of Kansas put it, because Iron-60 is radioactive, if it was formed with the Earth, it would be long gone by now. So it had to have been rained down on us. The same signature was found on the Moon. The same radioactive isotope, the same age. Whatever happened, it rained on everything. The ocean floor and the lunar surface alike. Scientists traced the likely source to the Scorpius-Centaurus stellar association, a cluster of massive stars sitting 300 to 400 light-years away. Over the past 10 million years, this association has produced an estimated 14 to 20 supernovae. The debris from those explosions has been arriving here, intermittently, ever since. 2.6 million years ago, Earth was not empty of large creatures. It was the late Pliocene. The oceans were full of marine megafauna that had existed for millions of years. And then, at approximately the same time as the Iron 60 layer, many of them disappeared. Carcharicles megalodon, the largest shark that ever lived, roughly the size of a school bus, vanished around this period. So did numerous species of seabirds, marine mammals, and turtles. Melot's 2018 paper in the journal Astrobiology proposed a mechanism, muons, cosmic ray muons from the supernova explosions, penetrating deep into the ocean, delivering elevated radiation doses to large marine animals over years to decades. The bigger the animal, the bigger the cross-section, the higher the dose. This is not a hypothesis about something that might happen. It already happened. The evidence is in the rock. The Iron 60 is there right now, sitting in cores drilled from the ocean floor, waiting in storage at the Australian National University and other labs around the world. Supernovae have already hit Earth, within the span of human evolution. The question isn't whether the dangerous universe can reach us. It already has. Number 1. We live inside the scar. Here's what everything on this list has in common. The Iron 60 on the ocean floor. The radioactive debris on the moon. The extinction of the megalodon. The thinning of the cosmic ray barrier in our local region of the galaxy. All of it traces back to the same source. The solar system does not live in a quiet, ordinary corner of the Milky Way. It lives inside a bubble. A cavity roughly 1,000 light-years across, carved into the interstellar medium by a sequence of explosions, 14 to 20 supernovae over the last 10 million years, that blasted a hole in the galaxy's gas and left our solar system sitting in the middle of it. We call it the local bubble. It's been known to astronomers for decades, but its implications take a moment to fully settle in. We don't live near a dangerous region of space. We live inside one. The violence came first, and we formed in the aftermath. The explosions that made the local bubble came from a cluster of massive stars called the Scorpius-Centaurus Association. Right now, Scorpius-Centaurus sits roughly 300 to 400 light-years away. It is the nearest group of massive, young, unstable stars to our solar system. It has been exploding intermittently for millions of years. It is not done. And inside that association, visible on any clear night in the constellation Scorpius, burning red in the southern sky, is Antares, a red supergiant, about 550 light-years away, one of the next candidates from that same association to go. It is not going to harm us when it does. It's too far away. But that's not the point. The point is this. When you look at Antares tonight, you're looking at the next explosion in the sequence that made everything around us. The bubble we're sitting in, the Iron 60 on the seafloor, the thinned-out gas that gives our neighborhood its slightly lower cosmic ray flux, the vast empty cavity that is our home, was built by stars like Antares. Stars that lived for a few million years, burned extraordinary, and detonated. And the debris of those detonations is in the rock beneath the ocean. It's in the crust of the moon. It's in the tree rings, and the magnetic field, and the satellite orbits, and the phantom stars that astronauts see when they cross over South America with their eyes closed. The dangerous part of the universe is not somewhere else. It is the context in which we exist. Every item on this list, from the anomaly 200 kilometers up to the bubbles of hot gas stretching 1,000 light-years in every direction, is part of the same story. We are not observers of a dangerous universe. We are inside it. We were built inside it. And we are, somehow, still here. Go look at Antares sometime. It's not hard to find. It's the reddest, brightest thing in Scorpius on a summer night. Just a point of light. The next scheduled explosion in the sequence that made our world. It'll go when it goes. We won't see it coming. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.